Hello, my name is Anthony, and this is my glider report. So for a description of this project, in this project we designed, built, iterated, and flew a balsa wood glider, and my glider's name is the Trader Joe's Pizza Glider. More on that later. So for the design requirements, the glider must be hand thrown and its only thrust can come from the throw. It must have wings, it must be less than 16 by 16 inches, it must be made primarily from balsa wood, and it must fly at least 20 feet in the thrown direction and cannot come apart. The first two are completion measurements, whereas the last three are numeric measurements. So for materials, I was deciding between using Play-Doh and metal coins for the added weight. The pros of metal are that it's denser, which makes it more aerodynamic, and also that it does not dry out. However, the cons are that they only come in select masses, and that they're more rigid, which caused damage to the front of my prototype. So because of this rigidness and that it only comes in select masses, I decided to use the Play-Doh. Then for the wing shape, I was debating on using a leading, trailing, or middle tapered wing. According to glider design physics camp, leading edge tapers result in best maneuverability, while trailing edge tapers result in best stability, and middle tapers result in a balance of both. So as a result, I chose a middle taper as it would give me a good balance. I also decided on using a middle taper because it would increase the glider's aspect ratio, which would decrease drag. Finally, I was deciding on whether I should have a dihedral angle wing. According to the FAA Glider Handbook, having a slight dihedral angle can increase lateral stability. I also found a DIY by Sheepy Anna that showed me how to create a dihedral for a balsa wing, but I decided against it as a dihedral angle would be difficult to glue together onto the fuselage and there's a large margin of error. Also, it would decrease the sturdiness and stability of the wing and therefore increase the chances of damaging the balsa wood glider. For the sizing, I decided to make my glider as large as possible to take full advantage of the wingspan and get the best aspect ratio. According to Aritra Saha, the horizontal stabilizer should be 20 to 25% of the wing area, and the vertical stabilizer should be to 40 to 45% of the horizontal stable area. So I followed these requirements. I also kept my aspect ratio in the 4.5 to 7.5 range as recommended by Glider Design Physics Camp. And then I put the main wing slightly in front of the center of the fuselage as I had stabilizers at the rear of the glider and I felt this would increase the glider's front stability. And finally, I kept the total length and width of the glider the same throughout the iterations. Here are the length and width measurements of my final design glider, which shows that it's within the requirements. For the initial design choices, I followed all the sizing dimensions from the previous page. I also gave the main wing a middle taper and I rounded off the wing and tail tips. Then I made sure the fuselage was a little thicker so it could hold the entire glider together. However, I made sure it wasn't too thick so it wouldn't increase weight and drag by too much. Then I also rounded off the fuselage's front and back to reduce drag, and I added a metal coin to the front of the fuselage so that the center of gravity would be closer to the middle of the wing. Here are the trials and test flight for my prototype. So the prototype was made out of thin cardboard, it used tape as an adhesive, and it was very asymmetrical. As a result, it was not sturdy and very unstable. It also became less sturdy and stable with each trial due to the crash landing. On most trials it did veer left, but it reached 20 feet on trial 9 when it flew straight. It also met all the requirements but the balsa wood and distance requirements, and the main aspect of improvement is its sturdiness and the stability. However, the prototype was very helpful and it went through a lot, so I named my final glider after it as a tribute. So for my next iteration, to increase its sturdiness and stability, I would use balsa wood and wood glue. I'd make the fuselage solid, and I increased the length of the horizontal stabilizers. Also to increase aerodynamics, I made sure the glider was symmetrical and everything was centered on the fuselage, and I added some Play-Doh to the front of the glider to move the CG forward. So here are the trials and a test flight for the next iteration. I took less trials because I didn't want the glider to break. So my second iteration glider was very sturdy and stable. It flew only slightly to the right, but it did pitch up and stall towards the end of its flight. However, it did meet all the requirements, and the main aspect of improvement is the CG of the glider. So my planned design changes were to add Play-Doh to the front to move the CG forward and under the main wing, and also to smooth the edges and tips of the wing and tails to improve aerodynamics and make the glider fly perfectly straight. So here are the trials and a video of my final glider. So my final design glider flew perfectly straight without pitch up or down and was very stable. I also found its CG by placing my index finger under the glider and it balanced on my finger at the 1/4 chord of the main wing, which meant the CG was there. The first design iterations drastically improved the glider's stability and sturdiness and how straight it flew, and the second design iterations drastically improved pitch and made it fly perfectly straight. The glider was also within all the requirements, as it was within the size limits, was made from balsa, had wings, was hand thrown, and met the 20 feet requirement on each trial. So for the coefficient of lift and drag, I first found my glider's weight, and then the planform area by splitting my wing into a small rectangle and two trapezoids and adding those geometries together. Then I found the wingspan, and I found the average velocity as I found the flight time for each of the 5 trials of my final glider, and I divided those by their respective distances and averaged those. Then I found the sea level density as according to the engineering toolbox, and I calculated the lift coefficient using the equation and inputs shown. Then I found the aspect ratio, and I found the induced drag by using the inputs and an Oswald efficiency number of 0.9, and finally I found the drag coefficient using the equation shown at the bottom. In conclusion, my glider flew about 50 feet on my best flight. I enjoyed this project very much from all the design stages, and I was also able to combine all the knowledge I've learned throughout the semester into this one project. As a result of the project, I've also increased my knowledge of the flight of gliders and my wood skills, and designing and iterating model gliders. However, looking back, I would have made some changes. First off, I would have reduced the fuselage length as my glider's fuselage was too long, so it just added extra unnecessary weight. I also would have made the taper on the front of the wing less because it's more important for the glider to have stability. However, overall, I'm satisfied with the outcome of my glider. Here are my references.